But let's get into polymorphism. Did that do it by any chance? No audio. Oh, that kills me. I gotta give it one more try. It's getting the audio here. OBS is getting the audio, it's just not streaming it. I thought this one wasn't working, but maybe this is how I was getting the audio. It's worth a shot. This is my last attempt at debugging. As we get started, sure. All right, so grabbing behavior, having shared code in a base class, that's a good start. But one thing that we're really after is polymorphism. What can we do with this feature now that we have this base class that's being extended by multiple classes? Polymorphism is one very powerful answer to that. First lecture question, we're going to start working with JSON today. In the second half of the lecture, your lecture question is going to be, given this class, this store class, with no actual functionality, you can add functionality for testing if you'd like, but what I really want is a to_JSON and from_JSON method. The to_JSON is going to return a JSON string in the format of a JSON object with two keys, cache and register and inventory, with the appropriate values of these variables. So it should be cache and register going to a JSON number, and then inventory going to a JSON array of JSON strings. And then from JSON should take in a string of that same format and set the instance variables equal to the values from the JSON string. So we want to go to and from JSON strings in Scala. Some of you have seen in 1.15, we've done this pretty extensively in 1.15, but how do we do this in 1.16 now that we have Scala to work with? Okay, a reminder of the Scala type hierarchy when we have all these inheritance. That didn't do it right. So we have this inheritance tree where we have our classes extending other classes. We have this type any, which is being extended by any ref and any val, and then all of the other values in Scala being one of those two types, except technically nothing which is both of those types. It inherits from any ref and any val. Any val are all of the things that are going on the stack. These are always passed by value, meaning when we set them, when we pass them in as an argument to a method or function or a constructor call, we're always passing them by value. So we're making a copy of the value and giving that to whatever method we're calling. As opposed to any ref, anything that extends any ref, when we create new any refs, they're going on the heap. And we're only working with a memory address for those. We're taking the memory address of that location in heap memory and then passing that around whenever we use that as an argument for a method call for a constructor or a function. We're always passing by a reference. So we're still copying a value, but the value that we're copying is the reference itself. So any change that we make inside that method call, we're going over to the heap, going to that object in memory, and modifying its state, potentially. I mean, we might not. We might just access it, but we can modify that state of that object and have that state reflected in the calling method across, so we can have changes reflected across stack frames when we're messing with heap space. Any class that you create is going to be in any ref. You write a class, it's going on the heap. Any object of that type, it's going on the heap. So whenever you write a class, it's going to be passed by a reference. So keep that in mind when you're creating classes, you're passing them around in your methods. Any modification made inside that method, you're going to see that outside of the method as well. The example we saw, one of the examples we saw last time was this health potion. Health potion actually has 6 different Scala types, and it is all 6 of these types simultaneously. The health potion is a health potion. It is an inanimate object. It is a dynamic object. It is a game object. Oh man, I still have a typo on the slide. Can't get this one right. It is an any ref and it is an any. It's every single one of these types. So an object of type health potion can be stored in a variable of any one of these 6 types. And this is what we call polymorphism. The fact that a health potion has 6 different types, it has many forms, that's where we get our polymorphism. Which still, okay, who cares? We'll get to why we care about this in a minute. But this health potion can masquerade as any one of these 6 types. It has many different types associated with it. And we can treat it as any one of those 6 types. So one limitation of this is that we can only access the state and behavior of an object that matches the variable type in which it's stored. So when we have potion 1 stored in a variable of type health potion, we have access to everything that's defined in the health potion class, everything that's defined in an inanimate object, everything that's defined in a dynamic object, game object, any ref, and any. We have all of that, every single piece of content that's part of that health potion class. We have access to it so long as it's not private or otherwise restricted access. Potion 2, which is in a variable of type inanimate object, no longer has the health potion specific functionality. So we couldn't say potion 2 dot volume because that's defined only in the health potion class. But we can still get its magnitude of momentum, which is a method that we defined in the inanimate object class. So we still have functionality with that from potion 1 and potion 2. Magnitude of momentum was defined in an inanimate object. So the potion class inherited that method, and it knows about that method as well. But as soon as we go to potion 3, which is a dynamic object, and try to call magnitude of momentum on a dynamic object does not have a magnitude of momentum, method. Even though this class, this object, potion 3, is a health potion, it does have a magnitude of momentum method. We cannot access that method when we're storing it in a variable of type dynamic object, because it's not defined in the dynamic object class. As soon as we store this health potion in a dynamic object variable, we don't have access to that functionality anymore. We only have access to the dynamic object functionality. You have a question?
Can you downcast to access that?
Yes, so you could cast this, you could convert that into a health potion and work with it that way. And there are various ways to do that. But as long as it's stored in a variable of type dynamic object, you can't access its inanimate object and health potion functionality. You could say potion 7 of type health potion equals potion 3 that, convert this to cast this to a health potion and store it in a variable of type health potion and then use all of the health potion functionality. It still exists in that object. We just don't have access to it when it's stored in a variable of one of its supertypes. So this won't even compile. You can't even run your code if that line is in there. But why? Why would we ever do this? So far, the only thing we've seen about polymorphism, about storing these variables in different subtypes, or different supertypes, is that it restricts the functionality, so why would we ever want to do this? So one thing is to make our code in other classes a bit cleaner. So we had this player class last time, which had a use ball and a use health potion method, which got us the functionality that we wanted. If we just want, say, a dodgeball game where you can replenish your health with pickups, this is going to be okay. But as we want to expand this game and we want different types of static objects, or inanimate objects, is we want different types of objects in a game that our players can interact with. We have to modify the player class every single time we want to do that. That's something we do not want to do. I mentioned last time in passing, it's a very important design principle of once we have the player class written and tested, we should never have to modify the player class again unless we're adding functionality specific to the player itself. If we want to add a new object to the game, we should not have to go back and modify the player class, because that has nothing to do with the player. The player will interact with that object, but we don't want to modify the player class. So suppose we have a very large code base, maybe we have 100,000 lines of code, not uncommon out there, that would be a small code base out there in the wild. And we want to make a change, and we have all these interactions like this, where I want to add one type to my game. And then I have to go into my player class and add a method there. Then I have to go into my physics engine and modify something there. And then I have to go to my graphics library and modify something there. And I have all these dependencies that just ripple through my whole code base. And I'm basically rewriting the entire 100,000 line code base just to add one little thing into my game. We don't want to design it in a way where we have to do that. We want everything to be independent of each other. And we can do that if we don't do something like this. So what we can do is change the player class to, instead of using a ball or a health potion, just have it use an item that takes an inanimate object. Now we have one method for every single inanimate object that we have created in the past, that we may create in the future. Any inanimate object that will ever exist ever, we're already done with the player class in terms of inanimate objects. We never have to edit this unless we want to add something specific to the player. We want the player to be able to do something different and add more behavior to the player. But if we just have them use an item, we'll have this method take an inanimate object. Now we're restricted a little in what we can do with that in this method, but we can just call the inanimate object's use method, because we know every inanimate object has a use method because it's part of the inanimate object definition. It's part of that contract. If something extends an inanimate object, it has to have a use method that takes a player. And then in our case here, we just want to call that use method anyway. So we actually don't even care that this is a health potion or a ball or whatever. We're just going to call the use method on it and let the health potion or ball or whatever future object this may be that we may want to add to our game sometime in the future, whatever it may be, we're just going to call its use method and let it take care of it. So for the ball, we overrode this use method. We implemented this use method to be launching the ball, using the player's orientation, launch the ball in that direction with velocity according to the player's strength. And for our health potion, we modified the player's health to have them heal their HP back up to a maximum of their max HP. Two completely different behaviors. One has to do with just the player's HP. They had a protest that started at 12:30 today. Must be done. They're changing the world out there. So we had this use item method. It's going to call items use method, and every item can have completely wildly different behavior. The ball has to do all about physics, the physics of the ball. The health potion has to do with the HP of a player. Completely different, but we don't care from this. We just have, okay, you have this inventory slot, you have your item in there, you want to use it. We're just going to call its use method and have that item do whatever it does, whatever it wants to do. Now we add anything we want to this game. We extend an inanimate object, and the player can use that item, and that item can have whatever properties it has when it's used. We can extend this player class a little bit further. We need to go another step here. And we can extend dynamic object, and I had to make a quick redaction here. I had super.velocity before. That actually didn't compile. I could not figure out why exactly. That shouldn't have worked, I thought. But we'll do this dot velocity to access the super method's velocity. And then I'll put an underscore here just to distinguish that this is a different velocity. I want to access that superclass velocity, but I'll access it with this now, and just give my velocity a different name so they're distinguished between each other. I still have to look into that, but super dot velocity, the only error was you can't do that. It said you can't use super on velocity. And even I searched it up and couldn't figure out why. I thought that should have worked. But anyway, so what I want to do here, what the change I made here is extend dynamic object from the player class, because I want my player to be able to interact with my physics engine as well. So I want my health potions, my balls, and my player to all be able to interact with the physics engine. And if I extend dynamic object, I can do that. And I'd say this is the I shouldn't say more, but another huge, powerful advantage of polymorphism and inheritance. One of the really beautiful things about object-oriented programming is we can store objects of different, the player. The list is supposed to have player here as well. We can store objects of different types in the same data structure. Now this we really took for granted in Python and JavaScript. Those languages just let us do this out of the box. But now that we are strongly typed and have to define the type of every single variable we create, those types have to match the variables. Well, how do we have a data structure with mixed types when that's the case? How do we have some data structure with potions and balls? Well, the answer is polymorphism. We're going to take advantage of the fact that a potion and a ball and a player, which I forgot to add to the slide, I added it up there but not in my data structure. And players, these are all dynamic objects, so I can store them all in one data structure of type dynamic object. So I'll put all these things into this dynamic object list, and guess what world wants? It wants a list of dynamic objects. I'm going to give my game world all those dynamic objects, and now I run update world through the physics engine, and that physics engine does not care that it has players, balls, health potions, or whatever else we dream up in the future. Does not care as long as we're extending the dynamic object class. Now we have physics applied to our potions, balls, and players. And we also have a lot of other functionality. So our physics engine just cares about dynamic objects, but that doesn't restrict us to adding all that functionality we just added to our potions, balls, and players. The balls can be thrown, that potions can be drank. It doesn't matter to the physics engine, but we were able to extend that functionality, still build out these very different dynamic objects, and still have them work with our physics engine just by extending the dynamic object class in multiple other classes.
Did you extend dynamic object in the inanimate object class? That way you can spread to the other one?
Yeah.
Okay.
Yeah, inanimate object extends dynamic object. I think I actually have that on the next slide, if I recall. At least maybe in a few slides, but I'll revisit that as well. So, any other questions before we keep going? So the physics engine definitely lives on beyond that assignment. But we're not editing the physics engine anymore. We're done with the physics engine, unless we want to add more functionality to it. But we can still have that physics engine work with anything we dream up in the future, as long as we're only concerned with collisions between dynamic and static objects, and then computing which face of the static object was collided with. If that's and gravity. If that's the functionality we want, we're done with our physics engine. If you did the bonus and you have dynamic object collisions, and you have that functionality as well, that's going to apply to any game. If a ball collides with a health potion, that bonus question, that code, takes care of it. Those are going to collide, bounce off each other, and do what they're supposed to do, without having to add any physics to the health potion and not adding any health potion to the physics. Those are two completely separate pieces of code. They're just linked through the dynamic object class. Okay, let's talk about overrides a bit. So when you create a brand new class, you are extending some behavior from any ref and from any, and some of that functionality includes a toString method and a .equals method, which is called when you call equal equal. Those of you coming from Java, I didn't even pay attention to it. I don't even know if I did it yet this semester. But if you compare two strings in Java, you never use equal equal. You always use .equals. We haven't cared about that in Scala at all. If any of you took AP, you should be bothered by that. You should be wondering about that. Equal equal in Scala does all .equals of whatever object we have, remember everything's an object, so everything has a dot equals now from any, even any vales, even what would be a primitive. So Scala just automatically calls dot equals from equal equal. So there's no worrying about doing dot equals with strings and worrying about the references. A minor note, but if you've seen that in Java, which you should have if you've learned any Java, we don't have that same issue in Scala. Equal equal does call dot equals. So when we create a new class, we do get these two methods. We get a toString and a dot equals method, which is called dot equal equal, and we get their default behavior. So the default behavior of printing one of our objects to the screen, one of our health potions in this case, is going to be to print the fully qualified object name. This includes the package and the name of the class, an @ symbol, and then I have to gloss over this. If you've seen Dr. Hertz and myself arguing before the quiz on Wednesday, this is part of what we were debating about. So be careful here. I call these memory addresses. They are not memory addresses though, but the JVM can take this number and uniquely identify this object and find it in memory. Yeah. Method, which compares the references. So if the references are identical, then it's going to say true. So for 1 and 3, these two potions refer to the same object on the sheet. So that one returns true. But the other one is going to return false, even though all of the values are the same. For our purposes, those are identical health potions. They're the same location, same dimensions, which I made the dimensions 0. Oops. Same velocity, same volume. Looks like the same potion, but they're going to be not equal with the default equal because it's comparing references.
So if you want to compare the values of those two, you would have to write a method to call that.
Right, and we'll do that in a next slide or two. We'll see exactly how to do that. So if I don't want this behavior, which often we won't want this behavior, saying equal equal to say, are these the same object in memory? It's useful information in some cases, but probably not so much. And printing out the actual memory address, or not the actual memory address, but it's a hash code that the JVM uses to locate it in memory. If they're related, but kind of not, it gets spotty. But if you think of them as memory addresses, I won't get mad, but Dr. Hertz will. So take that for what it's worth. He is more correct than I am, but my way gets us through this quicker, I guess. I don't know. So if we don't want this default behavior, which isn't entirely useful except in very specific applications, this number is really meaningless to us as developers, we can override these methods. So let's start with toString. We can go to that method, and just like we did for the use method, we overrode the use method from inanimate object to have balls and health potions behave differently when the use method is called. We're going to do the same thing here to have our custom classes behave differently when their toString method is called, instead of getting that default behavior. So for this, I'll override that toString, and this has to be identical. It has to be def toString of type string, return to string. We're going to override the existing functionality and replace it with our own. And I'll just print out the location, velocity, and volume. And in physics vector, the physics vector that you have has an overridden toString, so when you print out a physics vector, it's not giving you those memory addresses, or pseudo-memory addresses, I guess. It's going to give you the x, y, and z in the format that we expect from a vector because that toString method is overridden. So we can just say print out this vector, and we get it in the format that we want, a more human-readable format. We can do the same thing with dot equals. So we'll override the equals method. Oh man, it was falling down for a while. We'll override the equals method in the same way. We're just going to take an object of type any, so we can call equal equal on absolutely anything, and return a Boolean if those two are equal or not. And for this, we'll typically use a match case statement. We don't have to dig deep into these right now, but what this does is takes an object, it's kind of like a switch statement if you've seen those before, switch and then cases. We're going to take this object as an input and match based on its type. We're going to say if this is a health potion and the volumes of these two health potions match, we're going to say these are the same health potions. They're effectively equivalent for our purposes, whatever our purposes may be down the road. And then we're going to use the wildcard underscore to say if it's any other type, false. These aren't the same. A health potion can only be equal to another health potion. But we could have different types if we wanted to say a health potion and a super health potion are equal if the super health potion is half empty or half full or whatever. We could add that type of functionality as well with different types. For our purposes here, we're just going to use health potions are equal if they're equal volume, everything else not equal. Now when we go back to this example, our print lines are more human readable information, and our equivalencies are actually checking, okay, these are both volume 4, so they're going to be the same for our purposes. They're going to be effectively equivalent. If I have these two health potions in my inventory, and I'm worried about replenishing my health, I'm only looking at the volume. How much healing power do these things have? They both have the same, those are the same to me. But we do that by overriding. Override equals, override toString. So we can get rid of that default behavior, which doesn't really help us out in very many instances. In the jumper code base, like I mentioned this before, we'll start looking at this more. We'll really dig into this on Wednesday. We'll see how the different types of jumps work in the jumper game. If you play that game, I encourage you to play around with the game now that you have your physics engine. Play around with that and play around with the jumping controls. Jumping controls, they are fairly complex, and we'll see how to code that next Wednesday. For example, if you're walking and then you jump, you'll jump higher. If you're jumping and then you release the jump button midair, you'll actually decelerate and start slowing down. You won't do a full jump. You can do a double jump. A lot of the jumping mechanics that you would expect from a 2D platform are built into that. So we'll take a look at how that happens on next Wednesday. For now, let's look at how platforms are implemented. So platform extends jumper object extends static object. So platform is a static object, which means it has a collide with dynamic object method that takes in the dynamic object that was collided and the face of the static object that it collided with. Of course, we wrote a lot of code that calls this method in our physics engine. Physics engine is going to call this, but in the physics engine homework, this method did nothing. It was what we call stubbed out. It just didn't do anything. We could actually have that as an abstract method, meaning it doesn't have any implementation. Just like we had an inanimate object, the use method didn't have any implementation. We could have done that in the physics engine. It just would have made it harder to test, so I wanted to give it fake functionality, just an empty body. But now we actually want some behavior out of this. So we're going to override that method and actually add what should a platform do when a dynamic object collides with it. And now this code gets pretty simple now that we did all that work in the physics engine class object. In that physics engine, I'm going to say if it collided with the top, I'm going to zero out its velocity. I'm going to set its z location, zero out its z velocity, not its xy velocity. I want you to be able to do a sliding stop. And take the z location and set it equal to the top of the platform. So I want you to land exactly on the platform. I don't want you clipping into the platform. I don't want you stopping before the top of the platform. I want you to land exactly on that platform. Even if that collision with the exact face didn't happen on that frame, it happened mid-frame most times in most cases. I still want to update your z location. Then call the onGround method. So whatever this object does when it's on the ground, for the player class, I use that to reset the double jump. So I know that I can jump twice again now if I go into the air. So we call that onGround method to update the player to let it know that it landed. Now we get that behavior, and our physics engine takes over with the rest. We get to reuse all that code, get all that functionality in our game, and not think about physics when we're writing this code here. This code gets really simple because we did all the work in our physics engine. Same with walls. If somebody hits, I want these walls, and the way jumper works, it's the x-axis and then the z-axis, and y is irrelevant in the game. If somebody hits the negative or positive x of a wall, they shouldn't be able to move through that wall. Their x velocity should be zeroed out, and their position should be butted right up against that wall. That's the behavior I want. So I just say, if you hit my negative edge, set your location equal to that edge, that face, zero out your velocity, or positive x, zero out velocity, and set your x equal to the other side of this wall. So I get that functionality pretty easily because we already did all that work in Physics Engine. Physics Engine is already deferring, doing all these computations, calling this method, and then we just override this method and say, if the Physics Engine tells me somebody hit me, behave this way. And then if you're wondering about jumper object, I just needed unique IDs for each object in the game so I can update the GUI as you're climbing up. I need to be able to keep track of what platforms are on screen. This is the only reason this class exists, or else wall could just extend static object directly. We're not really gaining any functionality from jumper object. I just need a unique ID across walls and platforms just for the GUI's sake. Okay, any questions on that? Let's get through some JSON. So I'm going to introduce some JSON and Scala here. I'm not going to go very in-depth. I'm going to give one example of reading Scala, one example of writing Scala. It won't be comprehensive. This is one example in the class where I do expect you to read some documentation to go into the library that we're going to use and study what you exactly need for the lecture question and moving forward with the class. Whenever we work with JSON, read that documentation, figure out exactly what you need for that specific case. So with that said, let's talk about JSON. So JSON, you've seen this in 115, so as I took it here. JSON, not too complex. It is something we put in the first semester freshman course. It's not crazy stuff. It's based on these 6 types, which we've covered way more than 6 types so far in this class. We've covered more than 6 just in these slides that we touched. So just 6 types here: strings, numbers. Numbers can be floating point or integers. Boolean values, arrays, which are sequential data structures, and objects, which are key value stores, and then null, which we don't really use, at least in any examples that I give. So effectively 5 real values, different values that we can get. For 115's purposes, I can fit all of 115 JSON content into one slide here. With Python, if we want to convert from Python data types to JSON strings, that is JSON.dumps, the S for string, and JSON.loads if I want to take a JSON string and parse it into Python data types. In JavaScript, JSON.stringify and JSON.parse do the same thing. So we want to go from JSON strings to JSON strings, from JSON strings to Python and JavaScript data types. 4 methods total, and we got 2 languages done. Done. How do we do this in Scala, though? Python and JavaScript, the reason we could get away with this is their data structures allow us to store different types in them. So if I have a JSON string representing a list that has a number, a string, and another list, or another array, and I want to convert that to Python, well, Python just says, oh yeah, it's just a Python list, I got you. But what about Scala? What if we have this JSON string, completely valid JSON, it's a JSON object with a timestamp key storing a number, a message key storing a string, an ISS, this is an International Space Station timestamp, at that timestamp it was at that long. The ISS position, which is another object, and that object itself has 2 keys with values of strings. What Scala type do we convert this to? We have it as a string, okay, cool. But what do we convert it to in Scala? What Scala type does this map over to? So we have some options here. We go a map of strings and just take each value, JSON value as its JSON string value and knock it down like that. I mean, that'll work, but we got to work with strings at that point. Longs, we have a long here, but we won't be able to get this string and this dictionary in there. How about a map of strings to a map of strings of strings? That way we can, I don't know, these ones won't really work, but we have a map of string, a map of string to a map of string of strings. That'll get us the ISS position, but we won't be able to represent the other two values. We're kind of in a bind here. There's one option that does work. Everything in Scala is an any, so we can do a map of string to any for the key value pairs here. This gets us what we want, but then we can also use can methods. We can say, are these things equal? Convert these things to strings. That's all we can do. And get the hash code. Not really much we can do if we use them in variables of type any. So we got to think of a better solution here to be able to work with JSON in a strongly typed language. This is our challenge that we have here. So we can't mix these, but of course we can mix data types if we use polymorphism. Yay. So now we're going to pull in a JavaScript library. We're going to pull in the play JSON library. It's an external library, so it's got to go in your Maven, your pom.xml, and install it with Maven. We're going to use the play JSON library, which has types exactly matching the JSON types. This JS string, JS number, JS boolean, JS array, JS object, JS null. We have a type for every single one of the JSON types, and they all extend JSON value. So we can work with JSON values and not care which one of the 6 actual types it is. We're just going to work with JSON values. And now the answer becomes clear. We're going to have a map of string to JSON value. Now we can store all these values using those classes that are defined in that library. And each one of those 6 classes has functionality that you would expect from strings, numbers, arrays, objects, booleans, and null. So we have to get them as JSON values. And then from JSON value, we'll do a little bit of manual work to be able to get them in the Scala values that we want. So you can see already this is a bit more work than Python and JavaScript had us do. So let's read some JSON. We'll read that JSON from the previous slides. The very first thing we need to do, well, after we do our pom.xml, install the library with Maven and everything, we need to import this new library that we just downloaded. It's going to be the play.api.libs.json, and then we're going to use 2 classes for this example, the JSON value and JSON object. The JSON value class and the JSON object. The very first thing we're going to do, we have this response as a string, as a Scala string, formatted in valid JSON. And we're going to call it JSON.parse. The JSON object has a parse method. We're going to call that method, and that's going to return this. It's going to go through all the JSON spec and convert this into a JSON value for us. Now this JSON value is, in fact, or at least can be converted into a JSON JS object. But for our purposes here, we're just going to leave it as a value and just use it as if it were a JS object. And then the way all the methods of the JSON value class are overridden, we're going to get the behavior that we expect from a JSON object, a JS object. So the key notation for this one, a little awkward notation if you ask me, but we're going to take parsed, this JSON value that we parsed, use the backslash and then the key name to be able to get a JS value at that key, as long as this is an actual JS object, and that object has a key of that name and has a value stored there. That's going to give me a JS value, and then I can use these as methods to be able to convert it to the values that I want. And it's very, very important. Let me wait for them to leave first. But it's very, very important. Use as and not to. If you use to, it's going to break. If you use as, it's going to be fine. So you would want to do 2string right here. That would be our kind of natural implementation. If you use 2string, it's going to convert it to a JSON string, which is going to preserve the double quotes. It's very hard to debug. It's going to be a lot of off-star questions to be exactly that bug. But if you do toString right there, it preserves the quotes because it's trying to return it as a JSON string that you could send to another program for it to parse as JSON, and you need the double quotes to have it be valid JSON. As string is going to convert it to a Scala string without the double quotes. So that'll trip a lot of people up, but nobody in this room will be tripped up by that, right? We want to use these as methods. So as, and then as a type parameter, just like if we create a map or a list, we're going to use a type parameter in brackets, and we're going to put the type that we want to convert it to in there. So at message, I expect that to be a string. So I'm going to say get the value at the key message and convert it to a Scala string for me, and then I can store it in a Scala string. The next one, same thing, as I want it as a long, because that number is going to overflow an int. I'm going to convert that to a long and store it as a long. A long is a 64-bit integer, so integer overflows after 2 to the 31. This is going to overflow 2 to the 63. So we can store larger integer values in a long. Just
always use long, even if it like stored in a different.
you can always use long if you want. Just be careful with like auto-graded stuff. If I say int, it's got to be int because I'm going to store it in a variable type int. And then it just might break, just incompatibility, stuff like that. So just be careful with that. But yeah, if you want that to be your standard, I always use longs. It's fine. You know, at some level, you probably lose some efficiency, but you're not going to notice in most cases. And then finally, the ISS position. Well, I can convert that to a map of string. And now those three values that we kind of expect these to be in Scala, we can convert them to those types and parse all these values out the way we expect. And worth noting for the lecture question, you'll have to use an array. Array uses the same syntax, except you do slash and then the index number. So you can loop over the indices and be able to get those. And that's something that I am leaving for the documentation. There's a lot of good information in that documentation, including how to work with arrays. So let's write this JSON string. I want to write that string at the top of the screen, give in my timestamp, message, and location. And for this, my big method I'm going to use is JSONs.toJSON method. This is going to convert whatever value I give it into its JSON value type. So it's going to, if I give it an int, this method is very powerful. If I give it an int, it's going to convert it to a JSON number. Give it a long, it'll convert it to a JSON number. Give it a string, it'll convert it to a JSON string, or a JS string. I give it this map of string to string. It's going to convert that to a JSON object, or JS object. And I don't actually care what type is being returned here when I call toJSON. I don't care what type it is. I'm just always going to store it in a variable of type JSON value. So I don't even have to know if I'm giving it ints or doubles or whatever. I don't care. I'm just going to store them in JS values because I know whatever that returns will extend a JSON value. So I'm just going to store all these in JSON values. Then I'm going to create a map of string for all my keys to JSON value or JS value with all my values. And then one last time, call JSON.toJSON on that map to get that in one big JS value that stores all of my information. And then just like in JavaScript, I'm going to call it JSON.stringify to convert that JS value into a JavaScript, properly formatted JavaScript string. Again, very different than calling toString on this. We're going to call stringify to make sure we're conforming to the JSON standard to get everything in the exact right format. Where toString, probably the way, I'm just speculating, but I guess that the way the library is implemented, they would have it called JSON.stringify, but we can't guarantee that, and they gave us a stringify method. We'll call this thing. Notice that none of this works with any types that you define, because the library doesn't know about those types unless you extend I don't know internally what it would be, but you'd have to extend one of their classes and then override methods that says, if you're converting me to JSON or from JSON, this is how that should happen. So in your classes, you can write methods to be able to use this library and do that manually yourself. You can say, if I'm converting this to JSON, call this method, which is what the lecture question is. So we have another thing to download to Maven. And I want to point out the Maven repository. So far I've just been giving you the Maven stuff, and yeah, you can still find the play library. I have it somewhere in the repo, so you can grab it a few different places. But I encourage you to go to the Maven repository and search for the play JSON library and get the pom.xml, get that XML yourself with the dependency. There are tons and tons of libraries in this repository that you can play with. So if you have any ideas, any crazy wild ideas that you want to play around with, and you're wondering, hey, is there a library that does what I want it to do? Search for the Maven repository and say, is there a library to do this? Or just Google search Maven and then whatever you want to do. There will probably be a library out there. You can grab that XML, paste it in your POM, and get all kinds of libraries to do all kinds of fun stuff. Which brings us back to the lecture question. All right, have Friday, have a good weekend.